Hello, and welcome to another installment of Real-Time Math. In this video, we're going to count how many arithmetic progressions there are with elements in 1 through n for some integer n. And this is a slightly different situation from last time. Actually, it's kind of similar. So if you're not familiar with how this works, it's like the format of this is that I tackle a problem that I don't know the solution to. And this is sort of the same solution as same situation as last time, where this is a problem that I have thought about before, but I got kind of stuck. And now I just want to give it another crack with the added pressure of having a camera on me. And then you can see sort of the process of, discovering maybe, hopefully, a solution. So what are we going to count today? We're going to count the number of arithmetic progressions with entries in 1 through n. So for example, it's not so interesting for n equals 1, 2, or 3, but for n equals 4, there's already a bit of complexity because we have 1, 2, 3, 4. So those are our choices. Well, how many arithmetic progressions of length 4 are there? There's only one. There are 2 of length 3. There's 1, 2, 3, and 2, 3, 4. Of length 2, there are should be 6, I think. 4 choose 2, so we have 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and then 3, 4. And then there are 4 of length 1, 2, 3, 4. And we're going to count the empty progression. So I'll denote it with the empty set. And of course, when I write 1, 2, 3, I really mean the set 1, 2, 3. But it's really annoying to write the braces all the time. And so, we can just understand that this is not the number 123 or 234, but really a set of integers. Okay, so how many are there of like 4? How many progressions are there with the numbers 1 through 4? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So the number is 14. And if you notice, so there are 14 of them. If you notice, it's pretty much all of the subsets of 1, 2, 3, and 4, except we're missing 2 of them, right? We're missing 1, 2, 4, and we're missing 1, 3, 4. I think that's it. Are we missing any more? No. Okay, but as we get further and further, they're definitely less and less. So if we write n, so say we write n, and we have, so it's 1, 2, 3, 4, 5, say, and we have the number, I don't know, let's call it an of arithmetic progressions. Well, for the first few n, it's just the same as how many subsets are there on n elements of a set of n elements. And so it's 1, and then there's 4. Hang on, this is not 1, this is 2. This is the empty one and the progression of length 1. This has 4, this is 8, this is 14, and I believe that 5 is 22. We could write it out, but I think it's 22. And so the question is, how big, or what is the formula for a n? And so what I did is I just counted how many arithmetic progressions of 1 through n have length exactly k. With the idea being we could sum over all k and get a number for a n. So let's sort of count that first. So this is stuff I've already done, but then we're going to get to a little bit of a mystery that I haven't figured out. So let's call it P and K. That's okay. So P and K is the number of progressions of 1 through n of length k. All right, so how do we count the number of progressions? Well, a progression has to start at a certain number, and then it has to have a certain step size. So for example, the step here is 1, you're adding 1, and then it has a length k, and those are all the parameters those are basically all the parameters. So there's sort of 3 things that, like I'll give an example. If we set the step size to be, so if the starting point, which I call A, is going to be 17, the step size is 4, and K is, we'll say 5, then we have the entire, so this is length, step, and this is base. Then we have the entire progression, right? Because we have 17, and you add 4, so that's 21. You add 4 again, it's 25, 29, 33, and that's it. That's the, because the length is 5, so there's 5 numbers in this progression. Okay, so there's only 3 things you can choose in a progression. Now, if we already know it's of length k, then there's only 2 things we can choose in a progression. So the way that we can count this is we get from, we sum over all possible A. That would be a good, oh, I think we should sum over R, just kidding. Because the way I did it before was to sum over R. Well, so let's say, how big can R be? If we have a progression of length k, the biggest that R can actually be is, well, A would be 1. So how big can R be? Let's start with that. How big can R be? Okay, so we'll say A equals 1, and n minus, and we want n to equal, n equals 1 plus k minus 1 times R. And so that's how we solve for R. So R will be equal to n minus 1 over k minus 1. That's if in this interval 1 through n, we have A being 1, and we go all the way to n, and along the way we pick up k things. So k things. Okay, so and I guess it's a 4. Okay, so that's how big R can be. So we sum over all R from 1 through n minus 1 over k minus 1. Brackets here, floor. And now, once we've chosen an R, how many choices of A do we have? The answer for that is, once we've fixed an R value, we just need to make sure that A is between 1 and something that's not going to make R fall off the edge of the other edge. So, for example, if R is, here, well, what am I trying to say here? A has to be, it can't be smaller than 1 because it's the numbers 1 through n. And how big can it be? We just need to make sure that A plus k minus 1 R is less than or equal to n. So how many choices for, how many choices for R, or how many choices for A are there? We can just solve for this, right? So it's A is less than or equal to n minus k minus 1 R. Okay, so that's it. So A is between this and 1, so that means that there are this many choices for A. And so that's what we put in here, n minus k minus 1. Okay, that's kind of messy, but that's how many choices we have. And then in principle, this could just be summed over all k, and we would get these numbers. So actually, we're probably like already like 10 minutes into the video. And so far I've done nothing new. I've already made this computation. The question, or sort of what's mysterious, is that I took the sums and plugged it into OEIS, and you get sort of numbers like this. And up to, I think it's plus or minus 1, because I think OEIS doesn't count the empty progression. It seems to give like an interesting formula that looks quite similar to mine, but I'm not so sure how it happens. Okay, so if you go into OEIS, so by the way, OEIS is the online encyclopedia of integer sequences. And I recommend whenever you do anything that pops out an integer sequence, a sequence of integers, you might as well just stick it into OEIS, because it's really cool. You get, you get different things that this sequence will count. So I popped it in there, this sequence 2, 4, 8, 14, 22. Once again, I think minus 1. It was like 1, 3, 7, 13, 1 or something. And yeah, it gave this formula. So it says that the number of arithmetic progressions is 1 plus n plus sum m equals 1 to n minus 1, sum k equals 1 to n minus 1, m over k. So it's really interesting. It's an entire grid of floor. Well, minus this one, n plus 1 at the front. So what did we have earlier? We have 1 plus n. So 1 is this, so I guess an in our notation would be p n 0 plus p n 1 plus sum 2 equals, k equals 2 to n of p and k. But we found out that p and k is actually this thing, so we might as well just set it in here. It's sum of r equals 1 to n minus 1 k minus 1 floor of n minus k minus 1 r. Is that correct? Yes. And so somehow this is supposed to be the same thing. Well, how many progressions of length 0 are there? There's exactly 1. So these cancel out because it's just 1. How many progressions of length n are there? Well, those are the ones that we counted here, right? There's 4 of them for n equals 4. And in general, there'd be n of them for an arbitrary n. So that cancels out. And so we're sort of left with this. These two things are supposed to be equal. And it's somewhat interesting because they don't look super different, right? We should be able to sort of reconcile these two different sums. Except I haven't seen exactly how, but well, maybe it's not too hard. Okay, so the first thing is we can sum over the first outer sum sums from n equals 1 to n minus 1, and the second sum goes from 2 to n. And that's really easy to fix. We can, so let's start with this sum and try to make it into the top one. So instead of summing from 2 to n, we'll sum from k equals 1 to n minus 1. And so this becomes r equals 1 to n minus 1 over k, shifting the indices a bit. And then we have 1 or n minus kr. Okay. That's the first bit. Okay. Now, I seem like there's this floor in the top here that I'm like not sure if I can take out. I know you can take it out because just in notationally, summing to a floor is the same as summing to any number because you only take integer values of r. But then, for example, but then when I want to do this, like because the first part of this doesn't even. The first part of this sum doesn't even depend on k. So I want to say that this is n minus 1 over k, right? Am I allowed to say that, or because technically it was this? This is what it was before. It was n times that, and I'm not super comfortable with just taking things in and out of floor functions like that. I think in general you can't do that. One way of doing this is we could actually see if the sums are actually the same. So there's two ways that this could be equal. The first would be easier. It's possible. I'll just temporarily highlight this. The first is that this sum in here is actually the same as this sum for every index that we're summing over here. And the other way is that it's not, but the sums are the same. So somehow they even out when you sum over everything. And so we could try just fixing, so say like k equals 3 and n equals 4, or n equals, let's say like n equals 8 and k equals 3. Okay, so that should be enough to check some stuff out. Okay. So when n equals 8 and k equals 3, oops, we're going to have to probably, there's some notational problems here. Because the k in the top is not the same as the k in the bottom. Okay, let's fix that. I'll change all this to m. M minus 1. This is an m. This is m equals 2. Or 2. Yes, 2 equals 2 to m. And all this should be to m as well. M, m, m. And then we'll just leave r and k separate. Okay, so we'll say m is 2 and n is, or n, I'm just going to confuse myself. M, we'll say it's 3, and is, we'll not pick it, it's 6, 7. Okay, so then this sum here is sum from r equals 1 to, I'm using 4. So n minus 1 is 6 over n is 2. So r equals 1 to 2 of 7 minus 3r. And that becomes 7 minus 3, which is 4, plus 7 minus 6, which is 1. That's 5. And over here, on this side, up there, we have m equals 2 to n. Oh, wait, hang on, I'm counting the same one, this floor here. We have k equals 1 to 6 of m is 3, 3 over k floor. Aha. So this is interesting because what looked like a rectangle before. So I was thinking this is interesting because here we have sums that are like sort of partial. We sum from m to from m equals 2 to n, and r goes to something depending on m. So I guess I haven't fully worked this out, but I think it's a triangle, right? It's sort of like, and then on top it looks like a square because the first index doesn't, or the second index doesn't depend on the first index, but it does because this floor disappears, it becomes 0 whenever k is greater than n. So what does that look like? It's 3 over 1, 3 over 1, plus 3 over 2, plus 3 over 3, plus 3 over 4, plus 3 over 5, plus 3 over 6. And like I said, they disappear when, so that disappears, that disappears, that disappears. And so you really just have 3 plus 1 plus 1, which is 5. So that's interesting. Not sure if we confirmed anything, but we didn't disprove anything. And so it seems possible that these two sums are actually the same because the inside sum is the same. Okay. Well, let's then try looking at this further. Okay, so what do we want to show? And let's actually use the same indices now. So we want to show that sum k equals 1 to m. So we'll say m is less than equal to n. K, is it less than equal to m or it's less than? So for 1 less than equal to m less than n, we have this. So we want to show k equals 1 to n of m choose m over k floor is equal to k equals 1 to m n minus, it's k equals 1 to m minus 1. And then we have n minus m k. Is that right? Okay. Once again, looks really easy, and kind of sad that I am not seeing it. So by the way, the OEIS just states this as a fact, and it's like, oh, obviously this is correct. And it's not very obvious to me, but it may be very obvious to some people watching this. So you might be finding this quite infuriating. Did I miss a floor somewhere? It's m minus 1 over what is it? M minus 1 over, there's an n here. So this is n. This is n minus 1. 1 over k. Floor. Oh, that's not possible. M floor. Okay. Well, why don't we sum over all mk instead? That seem right? Because okay, there's two parameters here. There's an n and there's an m. So why don't we just write a big table on this end? This is very brute forcey. You can just write a big table. Okay, so this is n is n. Okay, so 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6. Okay, so 1 m. Okay, so when n is 1, then m is 1, and you can only sum over one thing. 1 over 1, that's 1. Okay, so 2, we have 2, k equals 1 to 2 of 1 over 2 floor, 1 over 1 floor. 1 over 1 floor plus 1 over 2 floor, so that's just 1. And then now 2 over 1 floor plus 2 over 2 floor, that's 3. That makes sense? Okay, so this is always going to be 1. So now we have a 2 over 1 floor, 2 over 2 floor, 2 over 3 floor. And so that disappears, and we just have 2, and there's 3. So actually, that's interesting because there's nothing actually it actually seems to be the partial sum of something. There's no reason why this shouldn't be true. And then we just need to care about what the next guy is going to be. So I'm pretty sure the next guy is 4, because that would make it work with our formula that we had before. And let's just see that. So it's 3 over 1 plus 3 over 2 plus 3 over 3. And actually, we did it over here, right? So that's 3 plus 1 plus, ooh, this is 5. Is that the same? Have I made a mistake? 3 plus 1 plus 1, that's 5. So 1 plus 3 plus 5 is 9. 2 plus 1, 3 plus 1 plus 1. That's 5. 4 plus, the observation being that in the next row, when we sum over the same thing, but we put 4 on the bottom, so we're summing over 4 things, it's 3 over 1 plus 3 over 2 plus 3 over 3 plus 3 over 4. All forward, all like this. And this one obviously disappears. So you really just have the same sum as before, so this should be a 5 here. And I realize that we haven't counted 0 here. Does that matter? Because of the index shifting. Oh. What are we counting wrong? It's 2, 4, 8, 14. The row here should be 1. This should not be a 4. It should actually be 2 over 1, 2 over 2. Something has gone wrong. Oh, what am I saying? This is just the n minus 1. So we chop off this. We don't count this. We don't care about that. Yeah, we don't care about that. And all of this is plus 1 because we didn't count 0. So what here? I'll make it more clear what I'm talking about. So maybe you guys are confused as to what I was confused about and then why I'm okay now. Let's move this whole thing over. And we put a 0 here. And of course, this is 1 all the way down. And this is P and M. P and M. So the table contains the values of P and M, at least the purported formula for them. And remember, we only sum up to M equals N minus 1. So we don't have this entire thing disappears. And let's just erase it. And now the sums do look correct because we have the partial sums here of 1, 2, 4. This is 1 plus 1, so this is 9, 10. So that's correct. And then this should be, no, is that 10? 1, 2, 4, 10? Is that it? No. 1, 2. Okay, I'm confused again. 1, 2, 4. It's possible the formula is wrong. I really hope the formula is not wrong. We want this formula, 2, 4, 8, 14, 22. 2, 4, 8, 2. So this should be 2, 8, 2. Okay. So, okay. I think that I've sort of worked it out. We shouldn't really be doing the indexing I've gotten all wrong. So k should go from 2 to n. That's still wrong. Okay, so the indexing is correct on this sum, but it's counting the wrong thing in our, it's counting progressions of length k plus 1. And that's why I messed this up. So everything does shift forward. I'm getting this backwards. Okay, I'm just saying this because everything does seem to work out if you do this. So there's one progression of length 0 for all of these, and there are n progressions of length 1. So we just put 2, 3, 4, 5, 6. Now everything seems to add up properly, right? Because this would be 1. So now everything seems to add up properly. We have 2, 4, 8. This is 10. 1 plus 4 is 5. Or sorry, not 4. It's not 10. It's 14, right? So this is 14. 5 plus 5 plus 4. 14. This should be 22. So we put a 5 here. And then what is this for 5 over 1, 5 over 2, 5 over 3, 5 over 4, 5 over 5. This is 1, 1, 1, 1, 1. No, this is still 1, 2, 5. And so that is 7, 8, 9, 10. 10 here. Oh, sorry. 5 is 10. So 6, 7, 10. Ooh, it's 25. That's not quite right. 25, 1. This is 1. This is still 1. This is 2. This is 5. Which would be 10. 4. 6, 7, 10, 25? There's no way there's 25. I said I'm pretty sure it's 22. I could count. We could count again, but I think it's 22. Here, let's make a diversion and count the number of progressions of length 5. So there's one progression, 1, 2, 3, 4, 5. And then there's a 4. There's 1, 2, 3, 4, and 2, 3, 4, 5. Of 3, there's 1, 2, 3, 1, 3, 5. 1, 4 doesn't work. 2, 3, 4, 3, 4, 5. I think those are 4. Of length 2, there's 5, choose 2. 5, choose 2, which is 10. And there's, so I'll put a circle to say that's a count. And of length 1, there's 5. And there's, again, set, which count is 1. Okay, so how many is that? 1, 2, 3, 4, 5, 6, 7. 7. 7 plus 10 plus 6, which is 23. Okay, so it's not 22, it's 23. This doesn't give 23, unless I've counted wrong again. But hey, we've also found that this is 10 choose 2. 1, 3, and 5. 1. It's not 3 and 5, it's 2 and 4. 1, 2, and 4. So maybe this is supposed to be 1, 2. This is mysterious. Well, I really do think it's 23. We didn't miss any progressions of length 4. There's just no other way you could fit a progression of length 4 in 1 through 5. With length 3, 17, 23, 24. 17, 22, 24. Okay, 23. Seems to be correct. 1, 2, 3. 1, 3, 5. 1, 4 doesn't work. 2, 3, 4. 2, 4 doesn't work. And then 3, 4, 5. That's it. So those are the 4 progressions of length 3. Then there's 5 choose 2 equals 10. Plus 5 plus 9 equals 23. So what's going wrong here? 6, 7, 10, 25%. 4 choose 1. 4, 1, 2, 3, 4, 5. That disappears. That's 1, 1, 2, 4. Ooh. Huh. Okay, okay. This is somewhere, wait. This is weird. That's a 4. N equals 4. We only sum up to n minus 1. So is there a 1 that's too much in all these? 4. Okay, let's try this again. It should be 4 over 1. It's n. It goes up to n minus 1. What am I doing wrong? This is n minus 1. So it's 4 over 2, 4 over 3, 4 over 4. It's 1. 1, 2, 4. That's 8. So it should be 8 here. So it works. Okay. What is the actual formula? It's sum. So in this table, a sum over the row here counts 1 plus n plus sum of k equals 1 to n minus 1 m over k floor. So that's the actual thing that we're counting in this partial sum. Okay, and so that's 20, that gives 23 here. And so we shouldn't be too far off now, I think. Because what do we just need to notice? Why is this the number of progressions of length? Okay. Well, there's two separate questions. The first question is, why does this count as many progressions? Which we could try to do now. Just literally see, what does 8 count? 8 should count something to do with progressions on 1 through 5. Okay, never mind. That's also not so clear. There's nothing here there's 8 of. This sum sort of breaks down to 1 plus 2 plus 4 plus 10 plus 5 plus 1. And there's no 8 in there. Okay, so that's not super clear. But maybe we can sum over a different way. What if, remember, we're kind of summing over what's another, so this is by length. So, but we could also sum over other things, like by step size, maybe. Okay, so let's count how many is a step, meaning the sort of intervals. So I'll count. So of step 1, this one, these are all step 1. In fact, I'm pretty sure they're all 1. Okay. Okay, what is that? How many is that? 1, 2, 3, 4, 5, 6, 7. There's only 7. That's also kind of sad. So there's if we counted by step, there's 5 plus 1, and then 5 plus 1, because this is progression of length 0, so there's no step. Progression of length 1 have no step, so we kind of just take that out. And then there's left here, there's 17 left, and we break them up. But the problem is, I think 16 of them have step 1, and only one of them has step 2. So it becomes sort of 2 plus 16. Sorry. 1 plus 16 or something. Plus 5 plus 1. Is it 16? Am I doing this count wrong? Counting 1, 2, 3, 4, 5, 6, 16. 10. Okay, and then this is the remaining guy that is step 2. So maybe it's not step. What about starting point? Okay, we were learning going through all the ways. So starting point, call it base, the base point. Yeah, maybe that's it. So how many have base point 1? 1, 2, 3, 4, 4. And of these 5, choose 2. We have base point 1, 4 of them. So 4. So there'll be 8. Oh, we're getting somewhere. 8 plus base point 2. We'll, we have 1, 2. And then how many here? It's not 4, it's 3. That's 5. Oh, I think I'm seeing it. Base point 3. There's this one. And there's 3 here. There's 3, 4, and 3, 5. Or sorry, 2 here. 3, 4, and 3, 5. That's total 3. How many at base point 4? None up top, and 1. Does that add up to 17? I think it does. And 8, 5, 3, 1. 8, 5, 3, 1. Oof. I think that's it. So this is counting how many. So we summed overall way back at the start of the video. I was like, oh, how are we going to count arithmetic progressions? Well, we can sum overall R, or we can sum overall K. And we decide, we can sum overall R, or we can sum overall A, the base point A. And I was like, oh, I normally sum this overall R, so let's just do that. But we summed overall A instead. Remember, we fixed K. And there are 3 things that determine arithmetic progression. The base point A, step size R, and the length K. And once you fix K, there's only 2 choices of what to sum over. It's either the base point or the step size. And we summed over the step size, which turned out to be the wrong thing to do. We should sum over all A instead. And if we would have done that, it's possible we would have just found this right away. Okay, so why not actually just let's spell it out. So the number of arithmetic progressions on 1 through n is 1 for the empty progression plus n for the progressions of length 1. So there's no step size to speak of. And then we sum over all a equals 1 through n minus 1. And once we fix an a, what are the possible choices for r? It's, well, that's it. It's r can go from 1 up to n minus 1 over k. Oh, hang on. What is it? So the constraint is that a plus k minus 1. Oh, are we summing over length here? Sorry. Oh, it's actually a little bit, okay, I feel a little better about not seeing this right away because we also summed over the wrong thing before. We were summing over k, which is the length of or we had fixed the k and then we were summing over the step sizes, possible step sizes. But I think what you do is you actually fix a step size and then sum over the possible lengths. Because yeah, okay. So let's say the step size is 1. Now, how long can it get? So we are solving for k here. So a plus k minus 1 r needs to be less than equal to n. So n minus a over k minus 1. R is less than that. N minus a over k minus 1. Oh, wait, we're solving for k. N, it's still n minus a over r. K minus 1 is less than equal to that. So k is plus 1. That's not right. N minus a. What's this pesky plus 1 doing here? Okay, let me reorganize my thoughts. Maybe this is just getting to the point where it's devolving into me being lost, but we've already sort of proven the thing. I think that so something over possible bases. We don't really care about the length. Length be whatever. We don't even really care about. We're just grouping by possible base points. So that's what we've done here. R can be as 1. I really think it's just it should sort of pop up that it's some kind of floor function now because you have this interval size n. N. N minus 1 equals 1. Okay, this might be related to some kind of weirdness with the floor function, where if you sum over all of it, you can actually think it's some kind of reciprocity. I've heard about it before, but I can't. The thing is, these videos are meant to be sort of I can't look stuff up, and so because I can't look stuff up, I may never just get this right. But I think that here's the problem: we do n minus. It's like n minus a over r, and we take a floor. And I'm wondering, and we sum over, is it n minus a? Pick the base point a. Pick the base point a. So now the interval we get is quite a lot smaller. It's n minus a long. I guess n minus a plus 1, maybe. And no, it's n minus a. Okay. And then we want to divide it into r pieces. We want to divide it into pieces of length r. Now, how many can we have? N minus a over r. Those are the possible lengths of this arithmetic function. Now we're like pretty much almost there, because if we sum over r up to n minus 1, which is the most you can have, 1 plus n minus 1 is n, then we have this. And so that's not that far off that. And I think there's some way you can just, or is it just changing the sum? N minus a, sum over all n minus a. N minus a goes from 1 to n minus 1. I actually think this is it. N minus a does go from 1 to n minus 1, right? Or it starts at, when a is 1, it's n minus 1. No, we're done. We can replace n minus a. Just that's it. So we've proven it. This does actually tell us that. So what we had before, where copy this. I think we've proven it. I mean, I'm sure that there will be some kind of. Let me know in the comments if this is actually wrong. But I think that it's not that off. That this is more or less a proof. This is supposed to be the same as what k equals 2 to n of n minus k minus 1 r. This thing. So taking that out, that's supposed to be the same for a given n. That I'm still not so sure about. But at the end of the day, I think there might be a way to prove this just from the series, like just like rearranging terms and stuff. But we've actually proven this inequality, right? Because this is, we're counting the same thing. This is counting all the progressions of length 2 and greater by summing over possible, like by summing over the lengths, and this is how many there are of a given length. This sums over all possible step sizes. And then we're done. Okay, no, that's not what I mean. And this needs to go back. So sum a equals 1 to n minus 1. This goes r equals 1 to n minus 1 over k minus 1. Right? So it's just all the possible ways you can have of summing over 3 things. Yeah, so this is you sum over the base point first, then the step size, then the length. So base, step, length. And this is you sum over all step, then length. And now this is how many base points you can have. And I think that's really the issue here. Okay, so I think we've done it. We've proved this, that the number of, okay, so I am happy with what we've done. We've proved that the number of arithmetic regressions in 1 through n is 1 plus n plus sum of a equals 1 to n minus 1, r equals, or k equals 1. Sorry. Is that k? No, it's r. Never mind. Sum of the step size, so r equals 1 to n minus 1. And how many lengths are there? There's a over r, 4. Okay. And I think that should be all for this video. I'm happy. The weirdness of the two formulas for something wasn't actually that weird. I mean, it looks kind of weird because the sums don't look like they can transform into one another. But when you think about how we're counting these progressions, then it makes sense. We're just counting them in a different way. And the mystery about why one is sort of a this is sort of a square where the inner summation doesn't depend on the outer one, whereas the other one does depend. That's actually just hidden in the for function here because these terms are all 0 whenever r is greater than a. Okay, so I think that's it for this video. And it's nice that we got something successful, although I'm sure that it's maybe not as fun to watch as it was to do. It was kind of there's kind of a mess partway through this video. But in any case, I hope you had fun, and I'll see you next time.